This is the second part of the lecture for Physical Science of Module 9. Okay, in part 1 of this lecture we learned how to calculate the speed of an object. So now we need to understand the distinction between speed and velocity. What is the difference? Well, as we learned, speed tells you how quickly an object moves. Velocity, on the other hand, tells you how quickly and in what direction the object is moving. Now, why is that additional information of direction so important? Well, imagine that I had 4 airplanes and their speed was all the same, 200 miles per hour. If their direction was as shown on this slide, there wouldn't be any problems. If, on the other hand, we had 4 airplanes going in these directions, again, they're all going at the same speed, but now the direction really matters, because if they're all headed at the same speed, they're all going to hit the same point at the same time. That would be a problem. So that is why scientists make a distinction between 2 quantities. One is called a vector quantity, the other is a scalar quantity. A vector quantity is a physical measurement that contains directional information. A scalar quantity is a physical measurement that does not contain directional information. So, since velocity does contain both speed and direction, it has this directional information, and therefore velocity is a vector quantity. Now, kind of a hint of how to remember that is that both velocity and vector start with a v. Now, there are other vector quantities that don't start with a v, but for what we're learning, that's sort of a helpful memory tool. Speed, on the other hand, does not contain any directional information, and therefore speed is an example of a scalar quantity. Again, it works nicely here that both of those start with the letter S. But again, there are other scalar quantities that don't start with the letter S. Now, to just continue to impress upon you the importance of direction, we get to do the fun experiment 9.1. First off, I need to let you know that on the second page of this lab experiment, I made an error, a mistake, and so on number 5, 6, and 7 on the second page of this lab report, change the 25 meters per second to 0.25 meters per second. This is experiment 9.1, where we're going to learn about the importance of direction. We're going to use some eggs here, and in order to make this a little more fun, we have given them character. So our first egg will probably be one that will be destroyed. She's sad. Okay, so that's one of our eggs. This one is the surprised egg, which is probably going to be destroyed as well. Here's the scared egg. It's going to have to roll down the ramp. And for some reason, ooh, that one looks kind of devious. So, okay, that's our eggs that we're going to use. Okay, we're going to do the first part of experiment 9.1. This is step 8 of the experiment, where we roll the eggs down the slide one behind the other. So here are 2 eggs that are going to do this part. We put them on the slide one behind the other, and they roll down. Okay, so what did we see in part 1, which was step 8 of our experiment? Well, they both were rolling down the ramp one behind the other. So their speed was the same, and their direction was the same. So what you need to record on your lab report is that the speed was the same, the direction was the same, and the damage in this case was probably 0 on a scale of 0 to 10. Now, if we calculate the relative speed, in other words, the speed of one relative to the other,
If we assume that they're traveling down the ramp at 0.25 meters per second, then the relative speed would be the speed of one minus the speed of the other, because their relative speed, their speed relative to each other, is 0 meters per second.
Okay, now we're going to do part 2, where one egg is sitting at the bottom of the slide. There he is. And the other egg is going to roll down the slide. There we go. Ready? Oh, do we have any damage? Let's see if we can see that there. Nope, he's still okay, but the one at the bottom of the slide, he's a little cracked up.
So let's talk about what we saw in that second part of the experiment, where one is sitting at the bottom of the ramp and the other one comes down the ramp and hits it. In this case, their speed is different. One of them has the speed as it's going down the ramp, the other one has no speed at all because it's not moving. Their direction is kind of different as well. One isn't moving, so it has no direction, while the other one does. So what you need to report on your lab report is that the speed was different, the direction is different, and the damage this time, I don't know, maybe about a 3 on a scale of 0 to 10. So when we compute the relative speed of these two, we have the one going down the ramp is going at 0.25 meters per second. The one at the bottom of the ramp is at 0 meters per second because it's not moving. Therefore, their relative speed, or the speed relative to each other, is 0.25 meters per second.
Okay, now I'm standing up on a chair looking down at the counter in my kitchen, and we're going to do part 3, where we have one egg rolling down one slide while the other egg rolls down the other side, meeting at the bottom. So we have our 2 volunteer eggs. They're ready to slide. Oh, they met at the bottom, and yes indeed.
That one's just fine.
That one was okay, but this one looks like it's time for scrambled eggs.
Okay, let's look at what we see in part 3 here. In this part, they're both eggs are going down a ramp that are at even height, and therefore we can assume that their speed is basically the same. Their direction, however, is completely different. One is going in one direction, the other is going in the other direction. So this time what you need to write on your lab report is that their speed is the same, their direction is different, and their damage would be maybe about a 7 on a scale of 0 to 10. So their relative speed would be 0.25 meters per second of one plus the 0.25 meters per second of the other. So we would add those two together to get the speed relative to each other, which is 0.5 meters per second. Now, if we look at the data from parts 1, 2, and 3, we can make a very important conclusion. When objects travel in the same direction, their relative speed is the difference between their individual speeds. But when objects travel in opposite directions, then their relative speed is the sum of their individual speeds. So in part 1, where the objects were traveling in the same distance, they both were going down the same ramp, their relative speed was 0.25 minus the difference, minus 0.25, to give us 0 meters per second. In part 3, however, the objects were traveling in opposite directions because they were on opposite slides or opposite ramps. Therefore, their relative speed was the sum, adding together the two. 0.25 meters per second plus 0.25 meters per second gave us the 0.5 meters per second for their relative speed. So let's put that concept, that conclusion, into practice here with an example. 2 cars are traveling down a road. The first car is traveling north at 55 miles per hour, and the second is a few hundred yards behind, traveling north at 45 miles per hour. What is their relative velocity? Okay, pause the video and write down your answer, and then turn it back on to see if you got it right. Okay, since they were both traveling in the same direction, they both were traveling north, then in order to compute their relative speed, we would subtract or take the difference of their individual speeds. So it would be 55 miles per hour minus 45 miles per hour is 10 miles per hour. That would be their speed. But the question asks for their velocity, and velocity has to include the speed and the direction, and therefore the relative velocity would be 10 miles per hour away from each other. They're moving away from each other. They're still both moving north, but relative to each other, they're moving away from each other. Okay, the last thing that we need to do for this lecture is to gather data for experiment 9.3. You're going to take that data, do some calculations with it later this week, and email me your results. So let's take a look at that.
Okay, this is experiment 9.3, where we're measuring height with a stopwatch. We're doing this in the entryway of my house, and right up here is Lauren, who's going to be standing up there dropping Emma's ball, and it will go down to the floor here. And then we're going to measure that with a stopwatch and do this 10 times and see what we get. So go ahead, she'll start the stopwatch at exactly the time she's dropping the ball, and then she'll stop it when the ball hits the ground. You ready? We're ready.
Okay, I'm not going to bore you by having you watch us drop a ball 10 times, but we did drop the ball, and here is the data that we gathered. Now you need to add in that these are in seconds. I put that under the time there rather than writing it in each box. So you need to pause the video and write down this data, because this is what you'll need to use for this experiment.
Okay, so we dropped the ball 10 times, so we'll get our average for that. And now we are measuring with our tape measure the height of our entryway. And what is it, Lauren?
160 inches.
160 inches. Okay.
So you need to record that data again on your experiment, on your lab report there. I've shown it that says the measured height of the ceiling. We were going to do this with the ceiling, but it's fine that we'll just assume that this is the entryway of my house. So that's 160 inches. So later this week, you're told to complete this lab report. You're going to have to do quite a bit of math here. So if you don't know how to do that, make sure that you ask a parent how to help you. And then you will email me the distance that you computed and your percentage error. If that is incorrect, then I'll return it to you and ask you to do it again. That's the end of the lecture. And now you can take quiz 9.1. Please do that on your computer and return it to me via email as soon as possible. Thanks a lot.